Electricity flowing through a wire creates a magnetic field. By the early 19th century, experiments by Ørsted and Ampere had already established this as scientific fact. But Michael Faraday and Joseph Henry looked at this relationship and asked the reverse. If electricity makes magnetism, can a magnet generate electricity? They tested this by connecting a coil of wire to a galvanometer, a meter to detect current, and placed a bar magnet nearby. If you hold that magnet perfectly still next to the wire, absolutely nothing happens. The meter stays firmly at zero. Current only appears when there is motion. When the magnet moves toward the coil, or when it is pulled away, electricity instantly surges through the wire. This is electromagnetic induction. The physical motion of a magnet near a conductor generates power, exactly what drives the electrical grids lighting our cities today. To measure exactly how much induction is happening, we use a concept called magnetic flux. Think of it like catching rain in a bucket. Flux is the total amount of magnetic field passing directly through a specific surface area. The first variable is the strength of the magnetic field itself. If you use a stronger magnet, the field becomes denser. More lines thread through the loop, and the total flux goes up. The second variable is the area of the wire loop. A wider loop captures a larger section of the magnetic field, increasing the flux even further. The third variable is the angle. If the loop turns sideways, the magnetic field lines slide right past the outer edge. Even with a strong magnet and large loop, if the field doesn't penetrate the center, the flux is zero. Magnetic flux is the interactive relationship between the strength of the field, the size of the area, and the exact angle of their intersection. Faraday discovered that simply having magnetic flux isn't enough to generate a voltage. The flux has to change. The speed of that change dictates the amount of induced voltage. Thrust a magnet quickly, and you get a massive surge of current. Move it slowly, and you get a trickle. There is a strict physical rule governing this interaction, represented by a minus sign in Faraday's equation. This is Lenz's law. The induced current creates its own magnetic field that actively fights the change in flux. Push a north pole toward the loop, and the loop creates a north pole to push back. If the coil always opposes the change in motion, what happens to the current when we stop pushing and start pulling the magnet away? The current instantly reverses. It generates a south pole, creating an attractive force that tries to drag the escaping magnet back toward the coil. This constant magnetic resistance is the conservation of energy playing out in real time. You must exert physical, mechanical effort to overcome the coil's opposition. That mechanical effort is exactly what gets converted into electrical power. The process relies on three interlocking rules. A changing magnetic flux creates a voltage, the speed of that change amplifies it, and the resulting current always opposes the motion that created it. This explains the physics of one magnet and one loop of wire in a laboratory. The engineering challenge is scaling that microscopic interaction up to generate electricity for millions of homes. By continuously rotating giant coils of wire inside massive magnetic fields, we create industrial-scale motional EMF. That rotation gives us the modern electrical generator, which we will break down next.